Hey everybody, we are continuing our study of forces in 2 dimensions, and there's a couple of things that I wanted to go over before we talked about inclines, which is what we're going to talk about next. But forces in 2 dimensions behave pretty similarly to all vectors in 2 dimensions. And so first thing I want to talk about is if I just have this line here, right? It's my vector. And what's going to happen here is I know that, for example, there's an angle involved. And so what this tells me is that there is both an x component, let's just call this first force, right? And there is an x component, horizontal, and then there's going to be a y component, vertical. And hopefully remember how to resolve vectors here, but basically the x component is simply the cosine of the angle, and the y component would be the sine of the angle at this point, okay? Now, the y component is not always sine, and the x component is not always cosine. There's lots of reasons why that happens, and we're going to talk about that actually when we study inclines. But here, what happens is that when forces are applied to an object, in 2 dimensions, you have to understand that it occurs kind of all over the place. And so what I'm going to do here is I'm going to draw a free body diagram here. And so it is a box being dragged across a rough surface. And so in other words, there's friction. And so I know that there is a force of gravity on the object. There is a normal force, right? The interaction between the floor and the object. There is, what's going to happen now is that there's a force being applied at an angle. I'm going to call that F1. And here's my angle here. And then, of course, I'll have friction pointing that way. And let's just say it has a mass of m. And so what happens here is there's a couple of kind of interesting things that happens. First off, I want to talk about the normal force. So if you notice, the normal force has these 2 components here in the applied force. Let's call this F1y and F1 in the x direction, okay? And we know it's the sine and the cosine of the angle here. But I want to talk about the normal force. And so previously, when we were talking about these objects, right, we had an object just sitting here, and if it was everything was happening in 1 dimension, right, the applied force and friction, and I would have the normal force and its weight. Well, these were always equal, quote unquote, right, because we knew nothing else was going on in the y direction. Well, now that's no longer the case, okay? So I want us to examine what happens in the y direction now. So let's just assume for a moment that the net force in the y direction is 0. In other words, the object doesn't accelerate off of the table. And for the most part, that's going to be the assumption that we can make. So what we're going to do is when we look at this, it's basically everything going up minus everything going down is going to be equal to 0. So the forces we're going to look at are going to be the normal force, this guy right here, the applied force in the y direction, and then our weight, or Fg. So those are going to be the forces that comprise the y direction. So we will have the normal force going up, the y component of the applied force, or that F1, the weight will go down, and we will set that equal to 0. And so what happens now is the normal force is no longer equal to the weight, right? So we're going to make kind of a big deal about that. The normal force is not equal to the weight anymore if there's this angle that occurs for the object. And so for the vast majority of the questions we're going to encounter from now on, that's going to be the case. So if we break this down a little bit further, we have the normal force. The F1 will be F1 sine theta minus mg is equal to 0. From here, we have basically all of the components of the forces involved to find the normal force. What's going to happen is when we use friction, remember friction is defined as mu times the normal force. And so when these problems happen that the force is at an angle, the normal force is going to be what we're going to need to use. And so the normal force here would equal mg minus F1 sine theta. What we would do is we would get this value and plug it into whatever we were talking about. And that's how we would utilize that to find the friction force. So friction force would look kind of funny. Friction force is mu times mg minus F1 sine theta. And that's how we'd be able to find the friction force, or perhaps we were needing to find mu. So algebraically, there's not too much you can do there that would be able to confuse you. Now, in the x direction, we have a couple of things we could talk about here. Let's first use the example that there's no acceleration in the x direction. So this comes up pretty straightforward. We have F1 in the x direction minus the friction force. And if I come back and look at my question here, there's nothing else going on here. So this would be equal to 0. And so there's lots of different things you can do here. This would be F1 cosine theta minus mu times the normal force. And remember, the normal force can be expressed using this, this idea. Oops, there it is. It's up here. Can be used using that big thing. So there's lots of different ways we can describe what's going on. You can also have an example where the net force is not 0. The mass of the object is accelerated. And so we would have something that would look like this. F1 in the x minus the friction force equals mass times acceleration. And so to fully expand that, right, it would look something like this. F1 cosine theta minus mu times the normal force equals mass times acceleration. And we could substitute the normal force, once again, to this big equation up here. And so there's lots of different ways that you can do these problems when you're talking about how objects accelerate and how they behave in the different directions. So let me know if you have any questions on that. The problem set is up and the solutions are up. Good luck. Let me know if you have any questions. Bye.